Thank you very much for inviting me to speak. The title of my talk is Quantum Acceleration of the Koopman-von Neumann Approach to Nonlinear Classical Dynamics. And I'd like to thank a number of my colleagues at Lawrence Livermore National Laboratory who are experts in quantum computing who were able to get a plasma physicist interested in this kind of stuff. So let me first tell you about the motivation. The motivation is that simulations of nonlinear classical dynamical systems are actually very important to understand the world around us. And yet we have this new concept of quantum computers that are emerging on the horizon. What we would like to know is, can we harness the power of future quantum computers for doing these kinds of calculations? And so in order to understand this, I'll first give you a little bit of a background on what quantum computing is about. And what we'll see from that is that we need to recast classical dynamics as a linear unitary evolution equation. And there are two different ways, two different natural ways of doing that. The first is to quantize the Hamiltonian system and then take the semi-classical limit. The second approach is to first take the semi-classical limit and then quantize. This other procedure actually also works for non-Hamiltonian systems. After telling you about this, we'll then consider what the complexity is for performing a quantum simulation of classical dynamical systems. I'll first remind you of what the important quantum algorithms are, and then talk about how we use Hamiltonian simulation and amplitude estimation to finally compute physical observables. So simulating classical dynamical systems is actually a very important, challenging problem. In fact, much of today's scientific computing power is devoted to these kinds of simulations. The quintessential type of simulation is an n-body problem that you might see in gravitation or plasma physics. We use those kinds of simulations to understand the large-scale structure of the universe. We also use those simulations to understand how to harness the physics of plasmas and harness the power of fusion energy for the benefit of mankind. We also perform these types of simulations when we simulate molecular dynamics, which we do in order to understand the biological function of proteins and molecules. So these are very, very important types of simulations. Now, the probability distribution function for n classical bits lives in a very high dimensional real vector space. That's because the overall number of states is 2 to the n. And that means that when we store and perform computational work on the entire PDF, that's an exponentially harder thing to do. Now, the wonderful thing about quantum computers is that they can potentially offer an exponential increase in both memory and computational power. And that's because the wave function for n qubits lives in a complex vector space of the same overall dimension. So it has an exponentially large amount of information that it can potentially store. In fact, it's just twice as much information as the classical PDF because it has both an amplitude and a phase. Now, the idea of quantum computing is that you could efficiently perform linear unitary operations on any superposition state. And that's where the real power comes from. So that leads directly to the question, can we formulate nonlinear classical dynamical systems in a manner that quantum computers can solve? And again, there are these two natural approaches, which I'll tell you about. Now, before we get to these approaches, let's think a little bit about, let me give you a little bit of an introduction to quantum computing. The way quantum computing works is really dictated by the postulates of quantum mechanics. The first postulate is that the wave function lives in a complex Hilbert space, and a qubit is the simplest non-trivial complex Hilbert space. So when we have classical bits, we have states 0 and 1, but a quantum state has this property that it can obviously be in a superposition of 0 and 1. Not only that, it has this really funny concept of a phase that it can be rotated around the axis connecting 0 and 1. So this is a qubit. theoretically. Now, experimentally, a good qubit has to actually be a nonlinear quantum oscillator so that when you are trying to work with specific energy levels, those transitions are individually addressable. And of course, it needs to be very well isolated from the environment in order to reduce decoherence. Now, one of the other really important postulates of quantum mechanics is that state spaces of subsystems are composed using the tensor product. And so when we have multiple qubits together, we just compose their state space in this natural way. The computational basis refers to the different measurement states that you can get. So like an arbitrary measurement is going to live in this high dimensional complex vector space. And again, the quantum state is just a superposition over all these possible computational basis states. Obviously, it's normalized, the overall phase doesn't matter. And again, that means quantum memory is very powerful. It can store an exponentially large amount of information. So let's try to understand the ideas behind quantum computing. Once again, we use one of the very important postulates of quantum mechanics. Quantum states evolve via linear unitary operations. And when we have a continuous evolution, obviously that means that we have a generalized Schrodinger equation where the wave function evolves via a Hermitian Hamiltonian operator. Now, there are actually a huge number of these potentially unitary operations that we can perform, because if n is the number of potential levels of the system, or the number of states of the system, then we get n squared possible unitary operations. So this is a large amount of things that we might potentially need to do. But the good news is that this very large space is generated by a very small number of basic unitary operations. We call that a gate set. The first example of that is given by the Solovay-Kitaev theorem, which says that when you look at the entire manifold of SU2, you can approximate that very well, essentially with two specially chosen single qubit gates. And then if you add just a single type of non-trivial two-qubit gate, that would allow you to construct all the other unitary operations that you need. And moreover, it only requires local two-qubit interactions, not even all-to-all connections between the qubits. So the general idea of what quantum computing is about is that many useful computations can actually be performed in a small number of unitary operations, that is, of order of some polynomial in the number of qubits, rather than this exponentially large number of states or unitary operations. The key resources here are quantum parallelism, this idea that you can efficiently act on superpositions, and interference, because we can use the phase to our advantage when we perform computations. Now, what are some of the limitations here? Some of the limitations are that, number one, approximating all unitaries is actually exponentially hard. So you can't just perform any unitary operation. Only certain ones can be done efficiently. Other ones would take an exponential number of steps. That also means that when you try to initialize the wave function, for the start of your quantum program, that can also potentially be exponentially hard, because all you're going to do is essentially apply a unitary operation to something like the initial state, typically the vacuum state. So that means that you can only prepare certain types of initial states efficiently. And very similarly, that means that measuring all the information in the wave function is also exponentially hard. Because, first, for one, there's an exponential number of things that you need to measure. But number two, you couldn't necessarily perform all those operations efficiently. So that means that only certain types of observables that are efficient should be measured. So now that we understand what quantum computing is about, you realize immediately that what we want to do is represent the classical dynamical system as evolving through a linear unitary evolution operator. This is going to be a representation that naturally maps onto the quantum computer. So the first approach is just to quantize the classical system, which we, know is a method that we all know and love. I mean, after all, the fundamental laws of physics are quantum, and that means that ultimately we're going to do something like solve a generalized Schrodinger equation. And if we're going to really solve this for a real system, that means that this is a pretty high dimensional partial differential equation that we have to solve for the wave function. And you can see that's a problem because the wave function if you just have some number of points per dimension, for the wave function, since it's a PDE, it's going to require an exponentially large amount of information, exponential in the dimension of the system. The beauty of the quantum computing approach is that the number of qubits you would need is only linear in the dimension of the system. Now, there are a number of advantages of this approach. The quantized system is often the more accurate physical model, and it's clear that a quantum computer could naturally be applied to simulating a quantum system. And perhaps less well known is that there are already quantum algorithms that can accelerate the computation of very useful classical quantities. For example, if you have a chaotic classical system, you can calculate the Lyapunov exponent, the diffusion coefficient, and if it experiences anomalous transport, these anomalous coefficients, more efficiently than you can using classical simulations. And you can see that in this image on the right over here. We're looking at a simulation of the quantum standard map, which is just an analog of Cherepov's standard map. And what you see happening is that as I increase the number of qubits, what I do here is I just initialize from a pure momentum state and watch what happens as the wave function evolves. And what you see is that as the number of qubits increases up to 16, then what the wave function looks like is something like a classical point array plot. And it's the ability of the wave function to really efficiently explore the phase space that leads to this type of speed up. So let me tell you about the very first quantum simulation of a plasma physics system that was performed by our group. We studied the nonlinear three-wave mixing problem, which is a classic problem in plasma physics and quantum optics. The general idea is that you have a Hamiltonian that represents the decay of a wave of type 1 into waves of type 2 and 3. And because the system is Hamiltonian, you also need the inverse process. So waves of type 2 and 3 can also recombine and form a wave of type 1 with an equal rate. Now, the fact that this system has conserved quantities, conserved action variables, which have to do with the different combinations of the numbers of waves in the system, that means that there's actually a very efficient quantum algorithm for simulating this type of system, which essentially is to use these to your advantage. Now we've actually simulated the system on this device here. This is called LNL QDIT. QDIT stands for a device that has more than two possible states. It has, in this case, it had 3 possible states that we were working with. And the evolution of this kind of system is a typical sort of nonlinear wave. You can see this wave over here in black. And you can see our experimental results in blue with these little blue dots here. And you see that over time, the little blue dots, they don't quite match the expected analytical curve. But we actually have a model for decoherence based on the Lindblad master equation, which actually pretty accurately shows this evolution here in the light purple. The way that we were able to achieve this for the first time ever was by using a special experimental technique called quantum optimal control. And what that allowed us to do was to compress something like 10 to 20 standard gates into a single unitary operation. And so you can see that we can get a number of oscillations on the order of 10-ish oscillations. In comparison, when we tried to do this on one of the standard available commercial platforms, the Rigetti platform, the data here is shown as the little red dots, and you see that you can execute about half a period, and then things fall apart due to decoherence. So that's just a plug for the fact that this other technique is quite useful. Now, there are issues with this approach, which depends on your application. So number one, taking the semi-classical limit actually requires simulating an incredibly large quantum system, right? And it's supposed to be something like Avogadro's number or more. But a second, more fundamental problem is that the quantum dynamics is not equal to the classical dynamics. There are many interesting effects which we learn about, in physics, right? There's diffraction, there's interference, there's tunneling. Perhaps, there are other also very subtle effects like the for example, dynamical Anderson localization. So if you have a quantum system, it may not experience as much chaotic diffusion as the equivalent classical system. Now, those differences, they appear on the very short Ehrenfest time, which is of order of characteristic time scale like the Lyapunov time times the logarithm of the size of the system. But you actually get major qualitative differences if you wait for the Heisenberg timescale, which is a timescale in which you can start to resolve individual energy levels. And some of the issues there, you don't have a butterfly effect. The classical trajectories and the quantum trajectories are actually reversible in time. And you can see that over here. Here's a typical example where you are simulating a classically chaotic system. At a certain point, you try to reverse the trajectory, and it starts going backwards for a little while, but after a while, the butterfly effect takes over, and the system just starts diffusing again. In contrast, when you look at the evolution of a quantum system, it can actually be reversed and exactly go back to its initial condition. But there are other issues too. The classical systems are not usually Hamiltonian. They won't necessarily have a natural or simple quantum quantization procedure. Like, for example, usually we're interested in simulating dissipative systems like the Navier-Stokes equation, resistive MHD, the collision-Boltzmann equation. We also are interested in simulating reactive systems that have instabilities, or like cases where you can get a growth, like reaction diffusion equation or neural network. In general, you can imagine that you might be able to do this by simulating a general open quantum system. But if you try to do that, there's something called the purification theorem, which says that you'll at least need to double the number of degrees of freedom, and hence you'll have to at least double the number of qubits. So that leads to trying to think about alternate approaches. And when you think about it, nonlinear classical dynamics is equivalent to the linear evolution of the probability distribution function. Let's just take a set of nonlinear ODEs that are first order in time, evolving via this equation here, x dot equals some velocities. And we imagine that the variables, they live in some potentially high dimensional real vector space. So one way that this would happen is if you have a large number of coupled particles, in a certain number of spatial dimensions. That's pretty large. Another natural way that would occur is if you numerically discretize a partial differential equation. If there are d spatial dimensions and you have a certain number of degrees of freedom per dimension, then you end up with an overall size of the system, which scales exponentially with the spatial dimension. Now, the way that we break this problem down classically is to recognize that we can actually solve the system trajectory by trajectory. And that's because any constant of the motion, such as like an initial particle label, that's just advected along the trajectory with this really simple PDE shown here. Now, there's another point of view which is complementary to this, which is that you can think about the advection of volumes on phase space, or probability distribution functions on phase space. And we can think about how that entire volume moves. Of course, that just moves via the adjoint equation, which is known as the Liouville equation. So the second approach is to express classical dynamics as the linear unitary evolution, something like a semi-classical wave function. And this goes all the way back to Koopman and von Neumann, and there are lots of later developments. But the basic idea is we're going to define a semi-classical wave function as something like the square root of the PDF. So we take the square root of the PDF and then we multiply it by a complex phase vector. The PDF is going to be assumed to satisfy the Liouville equation. And the phase is going to satisfy an equation of motion that just says that it's vectored along the trajectory, and that it has some source that's given by some specified phase-space function. And if we choose that phase-space function to be the classical Lagrangian, then when we have a Hamiltonian system, that will actually give us Feynman's prescription for the phase factor that we need for semi-classical dynamics.
10
so
minutes
given
left.
those two assumptions, you automatically find that the wave function evolves via the self-adjoint Koopman-von Neumann equation, shown here. And the interesting thing about it is it has this sort of symmetrized form of an advection operator that keeps the dynamics unitary no matter what coordinate system that you use. And this means the wave function itself is proportional to the square root of the PDF, or the square root of the Jacobian of the system. So this is a Schrodinger-like equation on twice the classical phase-space dimension, because we introduced these, conjugate momentum operators. It's Schrodinger-like because the equation is linear, and that means that it can exhibit features like chaos. It also means that there's no Heisenberg uncertainty relation for a simultaneous measurement of the coordinates. So we can just use these position eigenstates for the computational basis. So what's the meaning of this construction? What we've actually done is we've quantized the constrained Hamiltonian version of the dynamics. You can see that really easily because when you take the limit that Planck's constant goes to 0, you end up with a really simple classical Hamiltonian. And this classical Hamiltonian has our original phase space coordinates, but we also have these additional momentum variables, which are essentially Lagrange multipliers. They live in this extended phase space. And when we look at the action principle that you get from this, shown here, what you find is that when you extremize with respect to the Lagrange multipliers, you end up with the equations of motion that you wanted. And when you extremize with respect to the coordinates, you end up with a set of equations for the Lagrange multipliers that are really just there to keep the equations of motion symplectic. So now let's think about the complexity for quantum simulation of classical dynamics. There are many important quantum algorithms, which some of you may be aware of. The first really important quantum algorithm is called the quantum Fourier transform, and that gives you an exponential speedup from the typical fast Fourier transform down to n log n, where now n is the number of qubits instead of the number of levels. So that's a very powerful speedup, and it leads to lots of useful applications like the generalized Fourier transform on finite abelian groups and finite fields, generalized Walsh-Hadamard transforms. It's the key behind Shor's algorithm, phase estimation, discrete logarithm, integer factorization. So this is one of the key paradigms, and it's used. We'll see how it's used later. Another important algorithm is called amplitude amplification and estimation. That gives you a quadratic speedup. That's at the heart of Grover's search algorithm, but also more useful algorithms for our purposes like quantum counting and observable estimation. This algorithm has been generalized to something called a quantum walk. And again, this typically achieves about a quadratic speedup, and it can be used for a number of important things, including approximation of Hamiltonian evolutions. Now, synthesizing these building blocks leads to very useful applications. The most important one perhaps being quantum Hamiltonian simulation. And that was Manin and Feynman's original proposal, that we could use quantum computers to simulate the evolution of the wave function efficiently. And in particular, there's great hope that that can be applied to fermionic systems that we see in chemistry, nuclear physics, high energy physics. But we can also use it for other things that are important in scientific computing, like just solving linear equations. So it's thanks to the HHL algorithm down here, it's known that you can solve this linear equation with an exponential speedup in the sense that you prepare a state proportional to the solution. Now, for both of these approaches that I spoke about, Hamiltonian simulation and classical dynamics can lead to very large gains in memory and computational work.
Ilon, sorry, 5 minutes left, including questions.
Okay. Quantum speedup was already known to occur for solving linear systems of ODEs. And the question is, could you extend this to nonlinear systems? Well, it turns out that you can get up to an exponential savings relative to Eulerian discretization of the Liouville equation. And that's especially useful when the phase-space dimension is large. Remember, if we might have a large number of particles in a certain number of spatial dimensions leading to a very high overall dimension, then if we want to discretize the PDF, that leads to a very large overall dimension of the system, exponential in the original dimension. But thanks to this exponential compression, it would only require a number of qubits that is linear in dimension. Now, quantum simulation algorithms are known to be efficient as long as that Koopman-von Neumann Hamiltonian is sparse. It turns out that there are optimal methods for arbitrary sparse Hamiltonians. They require a certain amount of computational work that goes like the sparsity of the Hamiltonian times the number of qubits times the number of time steps relative to the fastest time scale in the system. And if you realize that the fastest timescales are set by kinetic energy, you get this scaling shown here. That means that you get an exponential speedup in the dimension of the system and a very significant polynomial speedup in the number of grid points per dimension because it's reduced by a pretty large factor. Now, the best classical methods are Monte Carlo and PIC methods. They're actually very similar to quantum algorithms in the sense that you use many explicit realizations to obtain an accurate expectation value. And the way they work is you just directly sample the observable by simulating multiple trajectories. But it's known that the way that this works is thanks to the central limit theorem. Whenever you want a certain accuracy, you need to sample a number of trajectories that goes like 1 over the accuracy squared. Now, it's already known that you can use quantum walks to obtain a quadratic speedup for specific state preparations that you might need for your initialization and measurement subroutines. So the real key then is to perform amplitude estimation of physical observables. That turns out to be up to quadratically more efficient than the best classical methods. What you're trying to do is compute an observable, the average of an observable. It's just the average of the observable over that distribution function. And you can do this by effectively calculating a wave function that looks like the square root of the observable times the Koopman-von Neumann wave function, as you also need to compute this complementary observable there, and you prepare a state of this form. The way that the quantum algorithm works is that you append an ancillary qubit, which starts off in its vacuum state to the overall system, and you perform this calculation that allows you to construct, compute this function, compute the complementary function. And what this does overall is to perform a certain rotation in a two-dimensional subspace of the system. What you can then do is use amplitude estimation of the ancillary one state. And what you get out of that is the probability sine squared theta, which is precisely observable that you're after. And you can do that with a complexity that goes like 1 over the accuracy that you need. So in conclusion, quantum computers can be used to efficiently simulate nonlinear classical dynamics on phase space. Quantizing the classical system works well for Hamiltonian systems, but it's not exactly equivalent to the classical system, and it would require a large Hilbert space. In contrast, the Koopman-von Neumann Hamiltonian exactly represents the semi-classical dynamics. You still need a large enough Hilbert space to approximate the classical system, and it ultimately requires doubling the phase space dimension and the number of qubits. And the main point here is that quantum simulation potentially offers very large gains over classical simulation. You can get up to an exponential speedup over Eulerian discretization and up to a quadratic speedup over Lagrangian discretizations. Thank you.